Good afternoon, everyone, and thank you so much for being here for today's iteration of our New Energy series, which is a collaboration among the Irving Institute at Dartmouth College and all of the universities and colleges that you see on this page to make sure that we have an opportunity for us all to learn from folks who are up and coming in energy and society research, and for them to be able to share their work with a broad platform, as broad a platform as possible. Excuse me. My name is Amanda Graham. I am the academic director for the Irving Institute, and it is my pleasure to welcome today Dr. Jorge Izar-Tenorio. I hope I'm pronouncing that correctly.
Yes, that's good.
From Carnegie Mellon University. Jorge is going to be speaking to us about this intersection between agriculture and irrigation and energy. Currently, Dr. Izar-Tenorio is a postdoctoral research associate at Carnegie Mellon, where his research focuses on understanding the dynamics of interdependent water, energy, and food systems under a changing climate and their implications on social, economic, and environmental outcomes, primarily in the Global South. He holds a PhD in engineering and public policy from Carnegie Mellon, a master's degree in sustainable energy technology from the Delft University of Technology, and a bachelor's in chemical engineering from the Universidad Autónoma de San Luis Potosí. So with that, please, Jorge, take it away. We're going to have Jorge's talk, and then we will have some time for Q&A. So please do throw your questions into the Q&A if you have them as he is proceeding with his talk. Really excited to hear your presentation. Go right ahead.
Thank you so much, Amanda. Hello, everybody. Today I'm going to present part of two research projects that I've been doing. One was part of the last part of my dissertation, and the second one was part of a project that I joined after I started my postdoc. I started my postdoc right after I finished my PhD, both at Carnegie Mellon University within the Department of Engineering and Public Policy. And this has been an exciting topic for us, and which we have been able to study a little bit, this double dividend between agriculture and electricity in East Africa, using irrigation as case study and using East African countries also as case study. So the first part is tells us that universal electrification, there is this notion that the universal electrification is actually part of a broad process together with other processes such as energy consumption, industrialization, especially in modernization, that actually lead to economic growth. We have seen case studies in countries over time, for instance, China and the United States here, that give us that evidence that electrification and industrialization actually occur pretty much at the same time, while the reliance on agriculture as share of the GDP actually starts to wane down. And this has been a trend in different countries, in this case, China and the United States. Obviously, it's not a perfect trend or an exact match for every case study, but the trend is there that when countries have more electricity access, they have also more modern practices introduced into their agriculture systems. They start to rely less on agriculture as share of GDP, and they start to diversify the economy, which leads to economic growth. The same thing happened in other countries, more emerging or non-industrialized, or let's say developing countries, such as Brazil, Mexico, or Thailand, in which the same thing happened. The reliance on agriculture started as share of GDP started to go down, while electrification and modernization actually started to go up. That's why we also focused a little bit more on agriculture in Africa, because Africa is one of the regions where most of the countries rely heavily on agriculture to generate GDP, and also employ a large percentage of the population in the agricultural sector on average. For instance, in the graph that we see here, we see that on the x-axis that the rural population And on the y-axis, we see the agriculture as share of GDP, and we see that most countries actually are on the rural, more the rural side, and all of them or most of them rely heavily on GDP compared to high-income countries. A 25% GDP on average in Africa is a lot compared to high-income countries, which actually only contribute around 1 to 2% to GDP from agriculture. And even some countries have depended on agriculture for employment. Up to 80% of their population actually is employed in agriculture. Sub-Saharan Africa, especially, that now focusing a little bit more on that part of Africa, is actually a region with very high potential, especially because they have, for agriculture, because they have a lot of water resources and they have a lot of uncultivated land that they can probably use or like start to develop a little bit more, and which has led in many ways or in many countries to relatively low yields, especially for staples, compared to similar regions in the world. So for instance, here in the graph on the left-hand side, we see that compared to Latin America or Asia, they have been lagging significantly in some of the most common staples. Also, this is partly because they haven't invested, or there hasn't been a priority for investing in modern practices such as irrigation or input supplies, or like modern input supplies such as fertilizers or seeds. In Africa or sub-Saharan Africa, most countries rely on traditional practices for cultivating crops such as rain-fed watering modes, or pretty much just the fertility from the soil. Sometimes they use some organic fertilizer, and the seeds have been traditionally also low yield seeds. And this, compared to other areas in the world, has also been lagging. And if we look a little bit more into the East African countries, we see that they have been, or most of them are a little bit behind the average in sub-Saharan Africa. Then we have another problem, which is the electricity axis, which in Africa is also quite behind other regions in the world. And even when in countries where they have some, like somewhat reasonably good electricity access, the consumption rates haven't been really there. And that's not a good sign for firms that want to invest in Africa. So for instance, in this case, Uganda, they have an electricity access of 24%, but the uptake or the consumption from that 24% is just 45%. Why? Because many people actually don't know what to use electricity for. So we believe that irrigation could actually bridge that gap a little bit and provide some more meaningful loads for electricity consumption. And why is that? Because we have seen evidence that when countries have access to electricity, then they start to consume a little bit more electricity per capita, and that leads to higher GDP per capita. And in Africa, still the electricity consumption per capita has been low compared to the world averages, and the electricity access as well. So that's why this study aims to answer three research questions. Like the first one is, what are the districts or in a high resolution, especially high resolution manner, what districts in Ethiopia, Rwanda, and Uganda have the highest techno-economic potential for investment in electricity and irrigation? And what other effects can irrigation have on crop productivity, land use, and electricity requirements in these three countries, so that they can have meaningful electricity consumption? And finally, why are we looking at electricity consumption? Because we feel that incorporating these productive uses of electricity into a least cost electrification planning could also influence the electrification mix. And then we focus, as part of the final part of this talk, it's going to focus a little bit more on that, using Ethiopia as a case study. So the three countries that I focused on in this study are Ethiopia, Uganda, and Rwanda. Why these countries? Because these countries have been among some of the fastest growing economies in sub-Saharan Africa in GDP per capita in the last 20 years. They also have a history of chronic hunger and famine, and project to experience severe food insecurity in the next coming years. And that's why they have been relying a lot on imports, on food imports, especially for staples to supply to their populations. So they present a good case of how irrigation can help some of these gaps. The analysis framework that I used is an integrated assessment model that combines agronomic, economic, and hydrologic factors. The first step is to use a biophysical crop growth model called AquaCrop that takes as input climate, soil texture, crop physiology, and field management data to simulate the yields and the net irrigation requirements of different crops. Then with that information, especially the net irrigation requirements, and we use that as input together with groundwater depth data and an irrigation network system that we define parametrically to estimate the electricity demand for irrigation using an engineering-based irrigation model. And finally, as another part of the model, just to add another layer, we want to estimate the water availability. It's a water balance model to estimate the groundwater recharge. And we call this the simplified hydrology model. The different scenarios that I studied for this for this study, were district level scenarios in the 3 countries, which they vary in size, but more or less the average size of the district are around 50 square kilometers. And we used historical data for 10 years, from 2010 to 2019, to evaluate the different variability in the rain patterns and temperature patterns. And we used three staple foods per country and 2 premium crops. So the 3 staple foods or the 3 staple crops in Rwanda and Uganda are maize, beans, and potato. And in Ethiopia, maize, teff, and wheat, both or all of them chosen based on the relative importance in each country. And then the 2 premium crops or cash crops, tomato and onion, as crops that may be suitable based on their economic potential as well. We use 2 seasons, rainy and dry seasons, and 2 watering modes, irrigated and rain-fed, both in the rainy and dry seasons. So sometimes the rainy season is not like rainy enough to supply all the water in that season. And as fertility levels, we use 4 fertility levels from low, moderate, near optimal, and unlimited, and low and high yield cultivars to also evaluate how different the irrigation can influence these two types of cultivars. Some key assumptions of this model or this study are that we use fixed planting dates for each country. The power source for irrigation is electricity coming from mini-grid solar PV. And we used the levelized cost of electricity for mini-grid solar PV in Africa specifically. Then the water for irrigation comes only from groundwater, not from surface waters, because groundwater is virtually available everywhere, and which is not in the case of surface water. There are no costs for rights or to extract water or licenses, no considerations for water quality or salinity. The phenology of the cultivars or the crops are modeled parametrically after literature of different crops in Africa. We also didn't consider topography or slopes. And the results that we found in terms of yields first in these 3 countries are that irrigation can increase yields by up to a factor of almost 4 for onions in Ethiopia. This is the maximum across the 5 crops. Up to a factor of 2 in Rwanda and for tomato, and a little bit more than 2 also for tomato in Uganda. That doesn't mean that the yields for staple crops are not good enough. And that just means that probably for these premium crops, the yields can be increased a lot more than for staples. But for staples, we see that there is actually a good increase in the yields, especially when we introduce these improved cultivars or high yield cultivars and high fertility levels. In terms of water requirements for the different crops, we evaluated the water requirements per ton. So here we don't want to see specifically some a high water requirement or a low water requirement, but more that the efficiency of the water usage in each of the districts or in some districts is actually good enough in combination with the yields so that we can actually have meaningful electricity loads, but not too high that the electricity loads are very high without having any benefits. So that's why we also have evaluated the electricity demand for irrigation in the different countries. And I'm going to ask you to keep this part in mind, because we're going to come back to this part for Ethiopia when I introduced that least cost electrification planning study. And this is why we focused very specifically on the electricity demand for irrigation, because we wanted to introduce that as productive uses of electricity in that least cost electrification model. We developed a metric called the levelized cost of irrigation to evaluate the financial viability for the different crops. The way to interpret this, this graph is to look at each one of the panels and the dots in the panels specifically, and compare them against the three dotted lines, the three dotted vertical lines in each of the panels. These three dotted vertical lines mean the minimum, the average, and the maximum crop prices in the last 10 years. Why do we want to compare against that? Because the levelized cost of irrigation gives us a price, an annualized price that I evaluated over a lifetime of 20 years for the irrigation system, and using discounted rates of 11%, 15% and 17% for Ethiopia, Rwanda, and Uganda respectively, and also considered some capital costs for the mini-grid solar and specific prices of electricity per kilowatt hour of electricity from that mini-grid solar. So each dot in each one of these panels, as the red and blue dots, actually mean an analyzed cost of irrigation. When we compare that against the crop prices, we see if it's more costly than the crop price, or if it's actually, we define financially viable when it's less costly than the crop price. So for instance, in these cases, we see, or I see, that onion and tomato pretty much for the three countries is shifted to the left of the dotted lines, which means that the levelized cost of irrigation for those three or for those two crops are actually financially viable. And that happens, as you can see in the panels, there are 4 rows in each panel, which are the different fertility levels with which we simulated the different crops. So we see, for instance, that for maize in Ethiopia, maize is marginally only financially viable, and only for improved cultivars, which are the red dots in each of the panels. And for instance, for beans in Rwanda, pretty much none of the dots in the panel are shifted to the left of the vertical dotted lines, which means that for beans in Rwanda, irrigation is not financially viable. Then, in order to assess a little bit more, or to add one more layer to evaluate viability, in this case, I'm going to call this techno-economic viability or feasibility, I added the water availability balance, and that we can see in the x-axis of the panels on the right-hand side of this figure. And with that, a district, I defined the techno-economic feasibility of a district when the LCOI, or the y-axis, is lower than the given crop price. The given crop price is underneath each one of the panels for each crop. So you see price per ton underneath, like for instance, Ethiopia teff is 850, maize is 200. These are the average crop prices also in the last 5 years. And then I defined that a district is techno-economically feasible when its LCOI is lower than a given crop price and the groundwater availability is 0 or higher. So the 0 is marked by the dotted vertical line in each of the graphs in the right-hand side. So that means that techno-economically feasible districts are usually found for horticulture crops in Ethiopia's central western part, Rwanda's western half, and Uganda's southeastern and northwestern. Pretty much all the purple colored places here in each of the panels or the maps mean that that district has good techno-economic feasibility for that crop. And oppositely, some of those that are colored yellow may not be actually techno-economically feasible, especially because they don't have enough water to supply irrigation, to provide irrigation. As another evaluation or estimation we did for annual electricity for irrigation demand, we aggregated only for the electricity consumption only for those districts that are techno-economically feasible. And we found that that irrigation aggregated over the whole country can make up to 17%, 65%, and 17% of the electricity and of the annual electricity consumption right now in Ethiopia, Rwanda, and Uganda. So this could be a huge increase in electricity and a huge meaningful load for firms to say, yes, there is good potential in these countries and there are good added benefits to invest in electricity infrastructure. Another benefit that it's probably a little bit harder to monetize that comes from irrigation is also that irrigation can reduce interannual yield variability. So this is very important for food security concerns, that irrigation actually for pretty much any fertility level can reduce that yield variability due to lack of rain in pretty much every district in each of the 3 countries. Now I'm gonna switch a little bit to the applications of the small scale pressurized irrigation work. That the first one that I did right after my postdoc was to help the Ethiopian Agricultural Transformation Agency, ATA, to identify areas with potential for agriculture and energy investments. Pretty much what we built the model for. It was a very simple way, or well, I had to expand a little bit the model such that I could include perennials in the model, because aquacrop didn't allow to model these perennial crops. But it was pretty much plug and play some of my model and to estimate the electricity requirements for different clusters that they had that ATA had identified previously, such that the idea for them is that they wanted to see first a high-level estimation of electricity consumption before they prioritize ground data collection on the ground, and to also before they invested in the scale-up phase of their mini-grid powered irrigation program. So we did this for 5 crops, or I did this for 5 crops, onion, tomato, avocado, banana, and mango. So we provided the data for around 600 clusters, rural clusters in Ethiopia. The second application of this first part of the study is the so-called, or the so-mentioned, least cost electrification planning modeling that incorporated productive uses of electricity for maize, and we prioritized ag clusters. This was, or is still, an ongoing collaboration with PhD student Charles Manheim, which is part of my research group at Carnegie Mellon University right now. And for this one, we had already identified, or I had already estimated the maize and wheat electricity requirements, and we just added them to residential electricity demands. So the modeling framework for this least cost electrification model was to first aggregate that electricity demand for irrigation to previously identified residential demand targets. Usually the way that these least cost electrification models work or have worked in the past in Africa is that they only include residential electricity demands to evaluate or to find the optimal mix of technologies to electrify a region. So with our work, we wanted to include those productive uses, in this case, coming from irrigation, to see how the optimal mix changed once irrigation was included or irrigation electricity was included. So for that, we used the estimated electricity demands that I found in the previous study as input data. We also used land cover data and crop statistics data together with what I had just mentioned now, residential electricity demand scenarios provided by the Global Electrification Program, GEP, for rural cluster settlements in Ethiopia, and also some electricity system parameters and geophysical variables that were provided also by that GEP data set for Ethiopia for those rural cluster settlements. And once we had all the demands together from residential and electricity demands at that high resolution for those rural cluster settlements, we used a model called OnSSET to estimate the least cost electrification technologies for Ethiopia. And then the outputs were the technology of electrification, the least cost electrification technology, then the levelized cost of electricity, and the investment costs in each one of these settlements. Some key assumptions on this OnSSET optimization model were that we didn't consider system reliability costs for the centralized grid. There were, we used pretty much only 4 or 5 types of technology to electrify. There were the centralized grid, standalone PV systems, and microgrid, mini-grid PV systems, and mini-grid hydro systems as well. We also considered or set up the model to force grid connections for clusters that were within 1 kilometer of medium voltage infrastructure. We also considered a 25% cost decrease for PVs by 2030. The evaluation time in the model was from 2018 to 2030. We also assumed grid generation costs based on the current 2021, or well, the 2021 tariff provided by the Ethiopian electric utility of 4.5 cents per kilowatt hour, which is heavily subsidized currently in Ethiopia. Then for the sensitivity analysis, we used different grid generation costs, and which, well, it's worth mentioning that their estimated cost, the real cost that some scholars estimate in Ethiopia is around 9 cents, so pretty much double that what the current tariff was in, or the tariff in 2021 was in Ethiopia. And one caveat from this OnSSET optimization model was that it's not possible to include electricity demands for productive uses on a year-to-year basis from 2018 to 2030, which it is possible to do it for residential electricity demand targets. So we work just with a single or an average electricity demand per in those 12 years. But the results show that adding the irrigation electricity demand into the model actually changes the optimal mix of technologies that supply electricity. So we see in the 4 maps that were the 4 panels, the top row shows the low demand scenario and shows also the 2 columns, and in the panel show the residential only scenario, only including residential electricity demand. And the second column includes the residential and the agricultural or the irrigation electricity demand, and how that the electricity mixes change by 2030 based on the different scenarios. Here we see that, for instance, the red dots in the low demand residential only demand scenario, actually a lot of the clusters that we did the study for are electrified by standalone PV systems. But then when we include the residential, the agricultural demand, then now a lot of those clusters actually transition to be supplied electricity by the grid. And we see as well that some of these clusters are actually electrified by mini grid, by PV mini grids, and which is also good news for firms, especially because there is a mini grid electrification program that is looking for investors in Africa. And then when we look at the high demand, that's even more evident that first the first part with only residential electricity demand was mainly supplied by standalone PVs, and then a lot more clusters and population and new capacity were supplied by mini grid, by PV mini grids and by the grid itself. So here's a little bit more of the summary of how the different clusters transition technologies in the low demand and the high demand scenarios from residential only to residential and agricultural demand. And we see that in a high demand scenario, as opposed to the low demand scenario, a lot of these standalone PV clusters are actually transitioning to grid or to mini grid, to PV mini grid. And we don't see, which was good for consistency in this study, any cluster transitioning from grid connection to decentralized connection, which was to be expected. Then when we looked at the levelized cost of electricity by 2030, we saw that including also the residential, the agricultural demand from the low demand scenario to the high demand scenario, the levelized cost of electricity on average for all the cluster settlements changed from around 44 cents to 19 cents per kilowatt hour. Obviously, the changes, as we see in the two rows, the changes were greater for the low demand scenario, but they were still a good sign for the high demand scenario that the levelized cost of electricity kept going down. So that's a good sign for also mini grid suppliers or for any other supplier that to see that the levelized cost of electricity, especially for users and the users as well, to see that they were not gonna pay a lot for electricity consumption. As a sensitivity analysis, we changed the grid generation cost, and this grid generation cost, in this case for the low grid generation cost, was set for 2 cents per kilowatt hour as opposed to 4.5 cents per kilowatt hour in the baseline cost, in the baseline scenario, sorry. And we see that a lot of the clusters actually change only to grid connection. That's because the grid is very, very, very cheap. But then when we use a high grid generation cost of around the real cost, 9 cents per kilowatt hour, then we see a lot more green in when we include the agricultural demand, and which is a good sign again, when the grid generation cost is actually closer to the real cost, then mini grid PV become more cost competitive against a standalone PV or the grid actually. So those are some of the high level summary or conclusions of our study, in which we found these are just the different scenarios that we modeled, and the total investment costs and the total capacity requirements in each of the scenarios, and also looking at what technology was supplying the different clusters and how much capacity was required for each of these technologies. So for instance, the population electrified by 2030 was the same in every scenario, the number of clusters as well, but the new capacity was significantly higher when the grid generation costs were higher. And also the investments obviously follow the same trend. And also that's a similar trend between the high demand and the low demand scenarios. That high demand scenarios were required a lot more capacity and also more investments. Well, the conclusions of these studies were that complementing small-scale pressurized irrigation with electricity infrastructure investments can actually improve electricity access and boost economic growth by providing meaningful electricity loads for firms to recover investments, and which we found by modeling how incorporating productive uses of electricity to residential electricity demands actually can change the optimal mix of electricity generation technologies, especially when the grid generation costs are more aligned to the real cost of electricity, of the real cost of generation by the grid. So thank you so much, and I open the floor for questions.
Terrific. Thank you so much, Jorge, for your presentation. I learned a lot in this presentation, and I'm really interested by your focus on the potential, right, for electrification to include not just the residential, but also the potential for agricultural benefits as well. So thank you so much for that. Folks, do send in your questions to the Q&A. And Jorge, if you want to maybe stop your screen share, we can be ready to pull up slides if there are any specific questions on specific slides that you shared. There were a couple of questions that came in prior to the talk, but I'm going to take moderator's prerogative and pose a couple of questions to you off the bat to get us started. The first is that you noted that in the initial scenarios that you were looking at, you built your climate models based on 10 past years, right, of rainfall. And so I'm wondering, obviously we recognize that there is a lot of change underway in our climate worldwide. And that has huge impacts potentially, right, on rainfall patterns, extreme rainfall events, extreme drought events. And so to what degree does your analysis have bearing on the world of 2030, right, or 2050, right? If some of the projections were based on past climate and rainfall data.
Yeah, that's a very good question, and thanks for bringing that up. Actually, that's something that we are currently evaluating as part of like my current duties as a postdoc. In that I am using projected future data to even not only to 2030, but like to mid-century and to the late century to evaluate how water requirements are going to change in different countries. Especially, I'm now finalizing a study in Ethiopia using all of these data from different general circulation models from different institutes in the world, and we're still we haven't yet integrated that into productive uses of electricity, but that's the plan, and hopefully we can have those results ready in the future to share here or to share with the audience in another way. And yeah, so I didn't include those in these past studies because we hadn't done the modeling using the data. So we did specify those assumptions or those bounds in our model so that we were sure to not mislead the audience that or the readers that that's not something that we were able to add. And also, especially because the model that we use for the least cost electrification technology, it doesn't enable us or allow us to supply year by year agricultural demand. So we only have to use a single point estimate. So that wouldn't probably be that useful. But anyway, I think there are ways around it. And hopefully in the future, we can provide the results for that study. Thank you.
Excellent, excellent. No, thank you. And I think it's, I mean, I guess partly my question is driven just simply by seeking to understand, right, how this is relevant in a, you know, with the changes that we're experiencing. But part of it is also, I mean, clearly an aspect that you're hoping for in this research is that it will be useful, right, to governments and to industry who are considering making developments. And those developments, if they're not on the ground now, right, what are the real circumstances in which they will be on the ground when an installation is operational, and how can they be assured, right, that their investment is going to be worthwhile, you know, in a new climate regime. A second question that I wanted to pose to you, or actually maybe it's just sort of a framing questions that I want you to be able to react to, is you mentioned a couple of times how part of what this study is able to do is to identify and describe opportunities for meaningful load, right? And so to make the case that there is an opportunity for electricity systems at some level to function and to provide a service, right, to the agricultural space, and then by extension to contribute to economic development. But I guess I wonder if you could also comment on what this other drivers, right, or other benefits, or maybe other concerns in the system, right, beyond just the techno-economic, right? So, in other words, what are the implications for local communities, right? What are the implications for farmers? What are the implications for people who live in the region? I mean, is there the capacity to sort of partner, you know, a very detailed modeling analysis like this with something that says, you know, are the farmers in these regions interested in irrigation systems, right? What kind of irrigation systems would work for them over time that they would be able to repair themselves if they break, right? So what's the sort of the socio-cultural feasibility of the kind of scenario, right, that this is testing and evaluating?
Yeah, I think that's a very good question. It's and that's been part of what I've been trying to also like open a little bit more the discussion about that with some of my collaborators and some of the other people on the ground, working on the ground too, is, and some of the discussions we've had so far are that, yeah, many of these like techno-economic analyses sound good in theory, but there is another part that also like sociological part that, for instance, how can we get from having electricity access and having meaningful theoretical loads to actually implementing, to actually educating people, or like providing different information to people on how to use this electricity. So that's a big part that I would like to see a little bit more science involved in that. And I still haven't had the time to work my head around that, but like, that's a good part that I would like to see. How can we go from just supplying the information to just telling, like educating the people? I've seen and I've read some literature about it, and at least in Africa, it seems like a lot of the successful cases for adopting irrigation technologies and using them have actually been or have happened with younger people. It seems like younger people are more receptive to being supplied the different information and being supplied the different technologies themselves on the ground than older people. It seems like older people are pretty much saying like, oh no, we already know our ways. We don't need anyone to tell us what we need to do. That's at least what I read about different successful cases. different irrigation technologies in sub-Saharan Africa. So that's
Well,
one point.
I think that, you know, just to add to that, I think that from a, you know, economic or community development perspective, you know, assessing the degree to which a community is interested in and wants development, right, is a precursor to whether or not that development is going to be successful, right, if it's coming in from the
Right.
outside, right. And so I think that it's one thing to do an analysis that could tell the potential, you know, feasibility for from an industrial perspective, but what does this solve the problems that the people on the ground identify for themselves, you know, or not, right? I think is another sort of big and open question.
Right, and definitely I see a lot of potential, but this is based on my more or my mind that has been educated in this more in these high income countries that supplying electricity or like supplying electricity infrastructure in these rural settings can also help with other parts of their development, such as I don't know, providing more night lights, or providing also electricity for their appliances. That has been another part of studies that I have been discussing with different groups. Some of the groups, for instance, want to focus more on electricity for cooking, because the cooking in Africa happens pretty much from wood burning, and that has a lot of health implications in houses. So this is another area where probably if we integrated that into the more irrigation part that I did, and say like what other applications or appliances can be used or can leverage that electricity infrastructure and can help people there. But again, same thing as you just said, we don't know if that's going to happen or not, because we first have to tap into that sociological part, I think. But I see the potential there.
A tremendous opportunity, I think, for multi-method, multidisciplinary partnerships, right? To bring that knowledge and perspective together, and to bring it into a grounded perspective, right? With people whose lived experience could be impacted. So going to a couple of questions here in the Q&A from Fazil Wamalwa. Apologies if I'm mispronouncing your name. The first question here is, have you factored in land use in these countries, like protected land and land currently not considered suitable for crop protection? Did you factor in the unavailability of those lands?
So initially, we didn't want to focus only on places that had crop production, or that were open for crop production only, or that were not protected, because we wanted to just see, like, we wanted to expand the model to every area. But definitely what Fasil is saying is a very valid like argument in like, or criticism, constructive criticism to this model. Yes, after we have done the modeling, we can start to filter some of those areas where actually agriculture is available or is suitable. And I think that's a very valid question in the future, to just include that and say, hey, these are the areas where we currently have agricultural activity, but we also don't want to lose some of that perspective that in which we may find areas where there is currently no agricultural activity that may be suitable for agriculture, and that maybe we may be missing if we didn't model the whole country. But that's a very valid argument.
Thank you. And a second question from the same guest, focusing on crop prices. South-Saharan Africa largely lacks formal crop markets for small-scale farmers. They mostly sell their crops to informal markets that are highly unpredictable. High crop yield results in price collapses, leading to huge financial losses. So did you factor this in when you were computing the economics of crop yield, the actual dynamics of the markets on the ground?
The short answer is no. We didn't factor the crop, like the nature of informal markets in the economic analysis. And why we didn't do that was because we relied on data supplied by FAO, like the farm gate prices for the different crops on a country level basis. That's one of the limitations of the study as well. Ideally, we would have liked to have crop prices on a district level basis so that we could actually compare more to those more like regional or local prices, because there is a lot of informal trading happening right now in the boundaries of countries as well. So sometimes even like, for instance, in Uganda is having like a drought and they're not producing enough maize. And then there is a lot of maize coming informally from Rwanda, which had a good rainfall year. So unfortunately, that's not well documented so far. And we cannot rely on just anecdotal evidence to do these studies. So unfortunately, yes, we don't have that information, or we didn't have that information and we couldn't include that, but that would be a great addition if someone could supply reliable data to just compare on like those crop prices at specific times, at specific points in time, so that we can compare those things together instead of just like relying on more theoretical, generalized crop prices.
Yep. Okay. We do have a question from an attendee who is asking for access to the deck because they would love to review the charts. So what I can say is that if Jorge is able to share his deck, we would be happy to post that on the Irving Institute website. So let us know, Jorge, and keep your eyes peeled on the Irving Institute website for that.
Well, I can say that the first part of the charts I can provide, we published a paper that I can send to you from the first part.
Excellent.
That's the part without the least cost electrification technologies. For the least cost electrification technologies, I cannot provide so far those charts because that's an ongoing research project that we are in the process of submitting to a journal. So yep. That's proprietary in that sense. I'm sorry about that. I hope that I can provide the DOI of that paper soon and provide those charts as well. But
excellent. So yes, please do send us the DOI, and we'll include that in the for the former paper, and we'll include that on the website. And yes, if you stay in touch, we will post it.
Thank you.
So before we wrap up, I have sort of a differently oriented question that I just wanted to pose here. When you were doing, and perhaps I missed it, forgive me if I did, but when you were doing the analysis about the lowest cost technology solutions, to what degree in your assessment did that track with the most efficient technology options, right? In other words, if we're going to electrify, that's great in its own ways, but how can we minimize, you've got these competing dynamics here. You want to show that you've got meaningful load, but at the same time, let's not just create, electricity for the sake of creating electricity. Let's make sure that we are leveraging, irrigation systems that are as efficient as possible, right? Because that's just a good first fuel approach. Efficiency is the first fuel, right? First fuel approach to this. So can you speak to that at all in terms of what you modeled?
Yeah, that's actually something that we filtered a little bit in the least cost electrification model in OnSSET, that we were using only electricity technologies that were clean electricity technologies. Well, except the centralized grid. The centralized grid, we didn't say this comes, we didn't specify where those decentralized grid electricity comes from. Right. So that's one caveat too of the model, that for that we only relied on the current portfolio of fuels in the country. But one of the main ideas behind the study was to look at only sustainable electricity technologies. In this case, we filtered also some of the diesel technologies that were also available in the model to be supplied by the model, and we focused only on natural resources such as sun, wind, hydro, and then the prices determined the optimal mix. But a good addition to this project would be to add some of the emissions or the life cycle assessment of each one of those technologies to see what's the more efficient technology. We didn't do that here, but hopefully that's an addition that we can provide in the future as well.
Well, I'm delighted to hear about your research agenda that you are crafting and to learn about these two studies. And indeed, there is a rich pathway ahead, right, for expanding on this analysis and pursuing further analysis. So, Jorge, thank you so much for sharing with us today this suite of work. You are one to watch, so we look forward to keeping an eye on how your research agenda develops over time. So, thank you very much for joining us today.
Thank you. Thank you all for your attention as well and the good questions.
Excellent. And so now just a quick note about our upcoming events. So we want to flag for you that our new energy series continues throughout the spring with young researchers. On the 30th of March, we will have Priya Donti, again from Carnegie Mellon, speaking to the topic of tackling climate change with machine learning. And then 2 weeks after that, in the middle of April, we will have Churchill Agutu from ETH Zurich speaking on how to scale off-grid technologies in sub-Saharan Africa. So keep your eyes tuned to this date and time space. And then on April 5, we are kicking off our spring series of the Dartmouth Energy Collaborative Energy Seminars with a seminar on energy, minerals, and materials, which is a really important nexus of challenges, and we'll be exploring that theme throughout the spring term in our DEC seminars. So looking forward to seeing you all there. Thank you very much for being here, and be well and be safe. Thank you. Bye-bye.